to talk about now this mysterious function. Deeper look at the objective function negative sigma delta ij ln of Pij. Okay. Let's think about a very simple case where we have some feature x1, x2, x3, x4, BMI 23, AC H1B value, I don't know, 6.3, and then something something. You have some feature value, okay? Yeah. And suppose for a given x1, x2, x3, 4, some fixed value, I'm not even going to state it. Let's say 5 are with label 0. Okay. 3 are with label 1. This one was the one that we were calling alpha. 2 are with label 2. Okay. Alpha, beta, gamma. Okay. And let's say that's all the data set that we have. Just 10 items, and we're trying to minimize this. What does it mean to minimize this? That's the question I want to answer. All right? So, let's think about the probability of a random element in this data set of 10 items. Are you with me? Is that okay? So we have 10 items, 5 belongs to 0, 3 belongs to 1, 2 belongs to 2. They have the exact same features, so there's no way to distinguish them, okay? So what would be the ideal outcome? The ideal outcome would be that any random element picked that has the same feature should have probability 5 out of 10 for this one, 3 out of 10 for this one, 2 out of 10 for this one, okay? I just want to see that this does do the job, okay? All right, so let's call this probability as x. That's the probability. Let's call the probability for belonging to this group 1 as y. Let's call the probability of it belonging to 2 as z. Okay. This y has nothing to do with the previous ones. This x has nothing to do with these. These are just numbers. And sorry for the confusion, but for the sake of calculation later, it's easier to do it this way. Okay. All right. So, what should x plus y plus z be?
1.
1. Because these are probabilities. Do you agree? Yeah. All right. So, x plus y plus z should be 1. Now, this summation is over all the elements, right? So let's do that. This one will be equals to negative. So first of all, if you pick one item from here, what should you be adding? 1 times ln of?
5?
No, probability.
X.
X. Okay? But then there are 5 of them, right? So as you add up all the 5 of them, what would you get? Negative 5 times ln x. Do you agree? All right. And then minus, how about this one? 3 ln y, right? And then it will be minus 2 ln z. Did you think? Right? So under this condition, we have this function. Now, since this is true, we can solve for z and say z is 1 minus x minus y, and replace the z here and then say, oh, this is negative 5 ln of x minus 3 ln of y minus 2 ln of 1 minus x minus z. Okay, x minus y, right. Now, assuming that this does have a minimum, when does it have a minimum? How do you find the minimum point?
Set it equal to 0.
Set what equal to 0?
The derivative.
This is yeah, but it's a function of x and y. What do you do?
Don't you use Green's theorem or something?
No, not Green's theorem.
Green's theorem.
Partial. You see, the gradient has to be 0. Okay. Yeah. So you do a partial with respect to x and partial with respect to y, and say equal to 0. And if you do that, you get exactly 5 out of 10 and 3 out of 10 and all that. Okay. So let's see. Just continue. Okay. So what is? Let's call this objective function f. What is f differentiated by x? Partial derivative. Well, ln of x differentiates to 1 over x. No, 5 times 5 over x, right? Because it's a partial derivative, this goes to 0, right? Okay. What about this one? It's plus 2 over 1 minus x minus y, because the chain rule, when you apply it, when you bring this out and differentiate, the only thing that contributes is negative x differentiates to negative 1, right? So it's negative 2 over this thing, because ln is 1 over. It's negative 2 over this, but then there's a minus 1 coming out from the chain rule. So this is what you get, okay? And I need this to be 0. In the same way, if you differentiate by y, you get
3 over 1.
3 over y, thank you. Yeah. This equal to 0. Okay? Is that okay? Yeah. All right, now you subtract. And that gives you, these two should cancel, and then what you get is, you get negative 5 over x plus 3 over y equals to 0, right? Move this to the other side, cross multiply. What do you get?
So the y.
3x.
Yeah, y is, let's see, y is 5, flip,
5 over 3x.
5 over 3x. Is that right? 5, no, 3 over 5x. Right? 3 over 5x. You should be able to do this mental math, right? So it's this one, and now you put it back into here, the first one. Okay? So you have, move this to the other side, and you have 2 over 1 minus x minus 3 over 5x equals to 5 over x. Cross multiply, you have 2x equals to 5 minus 5x minus 3x. Okay, move everything to the other side, you get 10x equals to 5. So what's x? 5 out of 10. Is this the value we want?
Yes.
Yes, that's the value we want, right? Is that okay?
Yeah.
Yeah. All right. What about y then? Y would be 3/5 times 5/10 cancels 3/10. Is that the one that we want?
Yep.
Yes. And then what about z? 2/10, because they have to add up to 1, subtract, you get 2/10. So this does minimize with the correct proportion. That's why we know that this objective function will train it in the right way to equally give you the proportion. But then that's just verifying that it's true. Now the next natural question is why? Why does it do that? Where does that come from? Like who invented that? Well, and then yeah, I have to leave some time for demonstration, so I'm just looking at time. I do have time. So let's see. So to understand where that objective function came from, well, the conclusion of what I'm about to explain is simply this. The objective function used for multinomial logistic regression is the negative log likelihood function. Okay, that one sentence is all you need to understand, but like that has so much stuff in there. Okay, so in order to understand what I'm saying, you first have to think about likelihood versus probability. So probability is like forward thinking. This coin has probability 1/2. Okay, if you flip it 10 times, how many of them will come out heads? 5 out of 10 is the most likely one, right? Yeah. So that's probability. Okay. Probability 1/2 says that if you repeat this, say 100 times, about 50 of them will be heads, 50 of them will be tails. Right? Okay. On the other hand, likelihood goes the opposite. What you do is you have a suspicion that there's this coin which is rigged so that it like gives you one more than the other, right? So you throw it 100 times and it comes out 67 times heads and 33 times tails. Okay. Then you ask, what was the original probability? Then the most likely probability that was there would have been 0.33, right? Or 0.67 for the heads. Yeah, you get what I mean, right? So in many cases, this is what's true. You have a probability function given by, well, whatever, like could be, you've learned some various probabilities in statistics, right? There was some binomial probability, there was like the Poisson distribution,
Geometric.
I don't know what that is. What's that?
Geometric distribution.
Yeah, right. Geometric and hypergeometric, those are, okay, yeah. So those are the things that you've learned, but then a lot of them also come with some parameter. Okay, so for example, the binomial probability distribution comes with n and p, right? Yeah. For Poisson, it just gives you a single value lambda, something like that. So let's see. Here's Poisson distribution with lambda. It's e to the negative lambda to the kth power over k factorial, where this will be k. All right. So here's the Poisson distribution for x, a random variable x to equal to k, for the parameter lambda. This lambda has the meaning of average occurrence in a time frame or something. But that's not important. Let's just say that you have this, okay? So if you view like this is probability. But then, yes?
Well, the lambda being like a coin flip, you can't really limit that, right?
Lambda is, it's not like, see, in the coin flip, I was putting p as a parameter, but it's totally different here. It's lambda, just think about it like this. It's a parameter. What does parameter mean? If you tweak it, the probability changes. Okay? But then, let's say we have some kind of an outcome, actual outcome, with this given probability distribution function. Okay? You observe some outcome, and then you look for various values for k. K equal to 0 has this probability, k equal to 1 has this probability. You have you can plot them, right? And then you can ask the reverse question. For this kind of distribution to occur, what should be the best lambda, right? What should be the lambda? So if you view this as a function of lambda for a given outcome, where this is the outcome, then this will be likelihood. So same function, when you view it as a function of your random variable, it's a probability. But if you think of it as a function of your parameter, it's called likelihood. Now, you might say, well, this looks like calling the same thing in two different ways. What's the difference? Well, here's the big difference. If you have probability, then if you select all the possible outcomes, add them up, then you should be getting 1, right? But here, you're thinking of this as a function of lambda, so if you think of all the possible values of lambda and you add them up, that has nothing to do with the actual probability, so this doesn't give you a 1. It's not 1, okay? And often what happens is like, the outcome is given, the actual distribution is given, right? And then if you look at the probability, the likelihood function given by whatever formula, it gives you values, it's still between 0 to 1, but there will be one peak in the likelihood function, right? And the peak is the one that you use to find the optimal parameter. Okay? It's called the maximum likelihood function, okay? So what you want is, let me just write it down. It might take a while for you to actually understand what I'm saying, or maybe multiple tries. So often, for a given output, given outcome, or set of outcomes, you want to find parameters, like the lambda here, that maximize the likelihood function. See, this outcome or set of outcomes is a fixed value, and you want to vary lambda and try to look at this, and you want to know which was the best, most likely scenario that happened. Okay? So you want to maximize the likelihood function, and that is called the maximum likelihood estimate. Maximum likelihood Sadly, because likelihood is not a probability, when you have maximum likelihood estimation, you really don't know what's the probability that, or confidence interval for your parameters. It'll be, maybe you can do it. Yeah, I guess that's in the, you may be able to do it, but I think that's the domain of Bayesian statistics, which I'm still learning those, so. Yeah. Okay. So, what are we doing here? So once you understood what likelihood is versus probability, now let's think about multinomial probability distribution. So here's a binomial probability distribution, which is n factorial over n minus k factorial, p to the k, q to the n minus k. Do you call this? Usually you just call this as n choose k, right? Yeah, that's the one that you learned. Multinomial is very similar. What you say is that you say m plus l plus k should be n under this condition, the probability of MLK is n factorial, m factorial, l factorial, k factorial, p to the m, q to the l, r to the k. Where these PQR is the x, y, and z that I was talking about in the previous one. There are three possibilities. So this will be the following case. You have a spinner that gives you three different values. Okay, alpha, beta, gamma. Okay, spinner with alpha, beta, gamma. Okay, and then you have a spinner. Like half of it is alpha, and there's like more beta than gamma, something like that. Okay. So you spin this, and then you want to spin this, say, 10 times. Okay. What's the probability that you get alpha 5 times, beta 3 times, and gamma 2 times? That's calculated like this. Is it okay? Okay. So, are we okay with this? Right. So in here, what are the parameters? The parameters are actually P, Q, and R. These are the N also, okay? Yeah, N, P, Q, and R. Those are the parameters, right? If you give me N, P, Q, and R, then I can write down the actual formula with all the numbers where it's ready to compute. Isn't that right? Right. If you don't give me N, P, Q, and R, it'll be just this formula we don't know how to compute for, even if you give me the values of M, L, K. But if you give me N, P, Q, R, then for a given value of M, L, K, I know how to compute. It's just this formula. Okay? So those are the parameters. So when you think about this as a likelihood function, it's a function of P, Q, and R, and also N. Is that okay? All right. Now, we make a few modifications here. This is just a constant, so you can just maximize this one. Okay. Usually, when you're given an outcome, you know the n, so that's not negotiable. Okay. So just remember what we did previously. We had like 10 data points where 5 of them were from group A, 3 were group B, group C was the 2, right? So if that's given, n is already given, so that's a constant that we know, so we don't really care about this. So when we say we want to maximize the likelihood function, which this is, as a function of PQR, we're really trying to maximize this one. Do you agree? So we want to maximize this, but then to maximize a function, you can maximize the logarithm of that function instead. Okay. Now, why do you do that? Well, sometimes these values become so small that computationally they might not be tractable. You see, probability, say 0.1, and then you have outcomes of 5. What happens is this becomes suddenly very small, and computers suffer with small values. Right? And because in probabilities that happens, and there are some other reasons which I don't fully understand, but that's like a very compelling reason for me. So you just want to take ln of f. So if you take ln of the likelihood, that's called the log likelihood function. Okay? Now what? Do you want to maximize this or minimize this? We want to know the maximum likelihood estimate for the P, Q, and R. Okay? Do you agree? Okay. So we want to maximize this. But that's same as minimizing negative log likelihood, right? Is that okay? All right. So now look, in the previous example, these were P, Q, and R was really X, Y, and Z. M, L, K were 5, 3, and 2. let's see what happens if we take negative log likelihood. Negative ln, okay, of p to the 5th power, q to the q happened 3 times and r happened twice. That's our log likelihood function. Okay, do you know the log rules? What happens if you have products?
You can add them up.
You can add instead, right? So you have ln of p to the 5th plus ln of q to the 3rd plus ln of r to the 2nd. Now, what's another log rule that you know?
You can bring the exponent down.
You can bring this in front. So what do you get? You get negative 5 ln of p minus 3 ln of q minus 2 ln of r. And now look at what happened. What is p? We called it x before, right? It's negative 5 ln x, negative 3 ln y, negative 2 ln z. That's exactly the function that we were trying to minimize. Okay? So now let me restate the statement I wanted to make. I made in the beginning. What did I say? Multinomial logistic regression is minimizing the negative log likelihood of the multinomial probability distribution. That's what's happening.